Okay, so we're looking here to solve the equation tangent 2x is equal to square root 3 on this particular given interval. So how do we go about doing that? Well, the new thing for us here is going to be this 2x, right? All of the other questions that we've had, we only had a regular quote-unquote x there. So this is something that's slightly new, but in all honesty, it doesn't affect a lot of what we do until the end. A lot of those early steps are exactly the same. So we'll notice that the trig itself is isolated. All of the other numbers, square root 3 in this case, are on the other side of the equation. So at the moment, we're treating this kind of like we did our inverse functions, right? Where is tangent of an angle? And we'll come back to kind of looking fully at this angle, right? But where is tangent of an angle equal to square root 3? Well, this is where our unit circle will come in handy. Let me enlarge that so we can read it a little better. If you remember, hopefully you do from our chapter 2 material, right? We have the tangent is only going to be in quadrants 1 and 4, right? Tangent inverse. So where are we going to have this inverse value equal to root 3? Well, tangent's a little less obvious, for lack of better words, because we just have sine and cosine values sitting in these ordered pairs. So we need to figure out where this square root 3 happens. And I do think some of us might see it faster than others, but don't let that slow you down, right? So remember, tangent's always defined as sine over cosine. So if we start with, say, this value right here, that is 1/2 divided by root 3 over 2. But if you remember, that's just multiplying by reciprocals, right? So I'm just going to actually write it like that. I'm going to say, what's 1/2 times 2 over root 3? Well, those 2's cancel, but that does not give us the root 3 that we wanted, right? It gives us its reciprocal. Here, if we divide, we get root 2 over 2 times, again, reciprocal, 2 over root 2. Cancel that, we get just 1. So tangent's 1 right here. Not that either. Here we get root 3 over 2 times 2 over 1. The 2's cancel, and we do get that square root 3 that we wanted. So this is the angle right here that we were looking for to get us to that root 3 value. Is that okay with everyone? Okay, so let me move this out of the way. So what that tells us is that tangent of our angle, and in this case our angle is 2x, is equal to pi over 3. Now, before I go any further, the other thing I want to acknowledge is I want us to remember that tangents, period, is pi, right? Remember, tangent's one of kind of the others, it's different, right? So when I'm thinking of this in general, and we kind of tend to default towards the general, remember we talked about the 2 different types in the last example, I'm going to write plus pi because that's its period, right? When we did the last question and we did sine, it's because we had to go around 1 full rotation before we could get there. So here, we're looking at pi over 3 plus pi. Now, this is where the new thing comes in. Remember, we had said this is different because there was this 2 paired with our x, right? Well, the ultimate goal when we're solving all of this, and maybe you write that off to the side, right? Your ultimate goal is to solve for x. That's what we always want to do in any given equation. So how do we solve this to get x by itself? Well, just algebraically, we divide everyone by 2, right? I'm going to put divided by 2 divided by 2. So this ends up giving us just x, which is what we were hoping for, right, is pi over 3, instead of times 2 or divided by 2, I'm going to say times its reciprocal and pi over 2, which gives us x is pi over 6 plus pi over 2. And one thing I forgot here is I need an n attached to this one, where n is an integer. So this represents the general solutions. We'll kind of highlight that here. This is in general, right? This is all angle, or all x values, I should say. All x values. But our question specifically said we want to look at answers that live on this interval, right? So we kind of take it an extra step and we say, okay, on the interval 0 to 2 pi, well, really a great approach to this is just plug in values of n. I know I won't use any negatives because that's going to take me smaller than I need to be, right? If I plugged in a -1 right here, that would take us to the negative direction. So I don't start there. We usually start at n is equal to 0. So then x, as a solution, I'm just going to plug in different values for this. So we have pi over 6 plus pi over 2 times 0. Well, that whole thing is 0, and we're left with x is pi over 6. That's one solution. So if you were to plug pi over 6 into your original equation, the 2 and the 6 would cancel out. Tangent 2 times pi over 6, and you'd be looking at tangent pi over 3, which is definitely equal to √3. That's how we know it's the answer. But we know the way trig functions work. There's a lot of repetition to this, right? So we keep going. So now you try, well, what's the next integer? 1. So we're looking at pi over 6 plus pi over 2 times 1, which is just pi over 2, right? So what's pi over 6 plus pi over 2? Well, we need a common denominator. We're going to multiply this by 3 and this by 3. So we're looking at x is equal to pi over 6 plus 3 pi over 6, which means x is equal to 4 pi over 6, or x is equal to 2 pi over 3. Now that's another answer. And notice we're still within that 2 pi rotation, right? So we do the same thing again. So now we try when n is equal to 2. Well, then we've got x is pi over 6 plus pi over 2 times 2. And you'll notice that these cancel, right? So we've got x is equal to pi over 6 plus just pi, again getting a common denominator, so let's put it over 1 times 6 times 6. We're running out of room here. X is equal to pi over 6 plus 6 pi over 6. Let me move here so we have some more space. Plus 6 pi over 6. So we're left with x is equal to 7 pi over 6. Now that is still within one full rotation under 2 pi. So this is also an answer. Okay, so you keep going. What about when n is equal to 3? Well, that's pi over 6 plus pi over 2 times 3. So we're looking at x is equal to pi over 6 plus 3 pi over 2. Again, we need a common denominator here. Times 3 times 3. So this is x is equal to pi over 6 plus 9 pi over 6, which gives us x is equal to 10 pi over 6. That's a really weird pi. Gives us 10 pi over 6, or if you reduce it, which you always should, 5 pi over 3. Okay, and again, you can see we're still within one full rotation. Now, I suspect, we'll verify this, but I do suspect that the next round of this will be too large. Okay, so let's try that out. So we've got now n is equal to 4, x is equal to pi over 6, pi over 2 times 4, which gives us, and again, we have some canceling that'll happen here, right? X is equal to pi over 6 plus 2 pi. Well, just as a point of kind of logically thinking about this, right? I want to stay between 0 and 2 pi. So if I add 2 pi to anything, I'm already too big. Right? Now, that may not be totally obvious. I know sometimes we get caught up in the question and we just want to finish, right? So this gives us pi over 6. Let me write in my times 6 over 6. That real fast. So we've got x is equal to pi over 6 plus 12 pi over 6, which means x is equal to 13 pi over 6, which is greater than 2 pi. And if you remember, this was kind of a maximum we were looking for up here. Okay, and I'm actually realizing now I will fix this for future questions. This should be a bracket, sorry about that, and this should be a parenthesis. So it should be 0, 2 pi. Okay, so we end up with 4 answers, 1, 2, 3, 4, and let me write them out. So our solutions on that interval from 0 to 2 pi, I just copied it wrong in my original question. I will definitely fix that for future ones. But our solutions here are x is equal to pi over 6, that's 1, 2 pi over 3, that's a second one, 7 pi over 6, a third one, and 5 pi over 3. Those are our 4 answers. You do not always have this many. We thought this was going to be an easy question, huh? You don't always have this many. However, you could. Some of why we have so many is because we're dealing with tangent, and tangent only has that period of pi. So there's less, there's less kind of movement happening, right? It's smaller increments. Okay, I will see you in the next example.